If you're the pessimistic type, you probably figure that humanity is headed for the exit. We're going to do ourselves in. We might do that with the nuclear weapons, just unleash them all, let them fly, and that would probably take us off the surface of the planet. Or maybe we'll use our biotechnology to make designer babies and sort of eliminate Homo sapiens, or just construct a pathogen that no medical interventions can stop. But the threat du jour is in fact climate change. Climate change extends for a century in front of us. We're not doing very well in combating it either. Is there any sort of experiment that might give us hope? Is there any way to know that we have at least some hope of having a longer L, if you think in terms of the Drake equation? Well, there is, and it's called SETI. Yes, if you do a SETI experiment and you pick up a radio signal or a flashing laser, or you see some sort of giant artifact like a Dyson sphere out there in space, you would know that at least that society was able to, survive their technological adolescence, to make a long-term go of it, and that would be encouraging. Now, if on the other hand you don't find a signal, well, that's a little bit ambiguous because you don't really know. Does that mean nobody was able to do this? That everybody wipes themselves out after they become a little bit technological? Maybe, but maybe they're just deliberately being cryptic. So the bottom line there is you can't prove a negative. And even though SETI is an imperfect crystal ball, it's the only one we've got.
Hello there, I'm Ross Andersen, Deputy Editor of The Atlantic. And in this session, we are going to be talking about habitability beyond the Earth, as Jonathan said, through the lens of the Fermi Paradox and the Great Filter. And as you all know, these are conceptual tools that emerge from the search for extraterrestrial intelligence, a domain of scientific inquiry that has sometimes struggled for legitimacy in a way that I suspect future historians of science will find perplexing. I've been working on a book about SETI, and in doing so, I often find myself evangelizing for it. And one of the things that people are often surprised and delighted to learn is that SETI scientists spend a lot of time thinking rigorously and creatively about how civilizations like ours evolve with their planets across deep time. And so I'm excited that that's our theme today, and even more excited to have with us for this conversation 3 scientists of the first rank who I will introduce now. And give a little wave, I guess, when I say your name. First, we have Dr. Jill Tarter from the SETI Institute. Second, we have Dr. Sofia Sheikh from UC Berkeley. And third, we have Dr. Sara Walker from Arizona State University and the Santa Fe Institute. Okay, I was hoping that to start us off, the 3 of you might each give us a kind of foundation for this discussion by sharing your perspective on the Fermi Paradox, this idea that our failure so far to observe intelligent life out in the cosmos is somehow surprising or requires explanation. And then I hoped you might tell us what you make of the Great Filter, the idea that one way of explaining the Fermi Paradox is that there's some difficulty latent in capital N nature, some filter that prevents planets, which we know exist in great number, from evolving into observable civilizations. Dr. Tarter, let's start with you. What do you make of these ideas as tools for thinking about SETI and for thinking about the fate of our species and planet?
Well, thanks, Ross, but you've started with one of my pet peeves, which is the Fermi Paradox, because there is no paradox, right? The logical structure of that argument is that if anywhere, anywhen another technological civilization had arisen, they would inevitably, very quickly evolve the capability for spaceflight. And then they would use that capability to populate all of the worlds in the galaxy anyway. And we look around and we say, they're not here. And the only way to get out of that is to say they never were anywhere, anywhen. But I think that's wrong, because I think we can't say they're not here, right? If you were interested in the question of, are there any fish in the ocean? You could take a glass and dip it in the ocean and then get it up here and take a look and see, did you catch any fish? Well, that's an experiment that could, in principle, work. But if you didn't see any fish in your glass, you're not likely to conclude that there are no fish in the ocean. You're likely to conclude that you haven't sampled enough of the ocean in order to have a reasonable chance of catching a fish. And of course, you'd miss all of the lovely fish that are much bigger than your glass. So I think that's where we are with respect to exploring for technological civilizations elsewhere. We just haven't looked well enough, long enough, and possibly in the right way to be able to make any significant statement about the existence of extraterrestrial technologies. So I don't like the term Fermi Paradox because we can't say they're not here yet. So I can't think that we can't construct a logical paradox.
Jill, I find myself quite sympathetic to your position, and I hope I tipped that off in my intro. But Sophia, what about you?
Well, first of all, totally agree with Jill on that one. You sort of stole my line of argument in a way there, so now I have to come up with something else. But actually, I think I'll take that opportunity to say, yeah, if you don't see any fish in the glass, the conclusion should probably be we need a bigger glass and not there are no fish in the ocean. And so that's something that we're working on. And the hardware that we develop, especially to do radio SETI searches or radio technosignature searches, which is what I specialize in, is developing so quickly, especially over the past couple decades, that we're able to, instead of going glass by glass, go, well, hot tub by hot tub. And that's only going to improve over time and accelerate how much of that search space we can look at. And so right now, it's very hard to say, how many extraterrestrial intelligences might be out there with these sorts of technologies, but we're starting to place those limits. And so I think this is a question that we can come back to in a couple decades or 100 years, and then maybe there will be a Fermi paradox. But until then, it's not maybe worth trying to conclude too much from our non-detection so far. And then on the point of the Great Filter, there's something very interesting here that I would love to talk a ton about, but I'll try and keep it brief, which is that as we move through human civilization, the things that we are anxious about, the things that Seth mentioned in that intro video, things like bioengineering pandemics or climate change or things like this, change. And they're often related to anxieties about what our current technological capabilities are and how that could go wrong. So from papers in, say, the 80s and 90s, you see a lot of anxiety about nuclear annihilation. And so there were SETI papers thinking about, like, okay, maybe that's the Great Filter. As soon as you get the capability to build nuclear weapons, you blow yourself up, and that's why we haven't found any extraterrestrial intelligences. And now, if you look at a lot of the existential risk literature, you see people talking about artificial intelligence. We're going to create an AI that goes rogue and destroys humanity. And maybe that's why there's a Great Filter. And so I think a lot of the different scenarios that people construct for what technosignatures we're going to be able to detect and what ways that civilizations might kind of traverse through their lifetimes and eventually end are very much related to where we are as humans. And you can see this as well with atmospheric pollution and climate change, which are also very prominent in the current SETI literature. And so I think that's where we need to make sure we're incorporating the perspectives of people in the humanities, of historians, of science and technology scholars, to make sure that we're not carrying these biases around without being aware of them.
And Sara, what about you?
So I also agree that the Fermi Paradox and the Great Filter might be ill-posed, but perhaps for different reasons than what Jill and Sophia pointed to. And the reasoning that I have really is that there's a lot of assumption that we understand what we are. And therefore, when we're looking for other examples of the phenomena that we are in the universe, we think we know what we're looking for. And I just don't think that's accurate, because I think we're very close maybe to developing a theory that is a more fundamental understanding of the nature of life and intelligence in the universe. I hope we're close, but we don't have it in hand yet. And so just as sort of an example, we did make first contact a few years ago with a phenomena that we predicted existed, but we had never detected in all of human history before even the history of our entire planet, which was gravitational waves, right? And gravitational waves permeate the entire universe, but unless you have the theory that predicts their existence and the technology to actually go out and detect them, you can't make contact with that phenomena. And I think we're premature in thinking that we're going to be making contact with alien intelligence, because we actually don't understand the nature of that phenomena, and we don't yet have the technology for making that contact. Although I think the sort of efforts that have been built up over the past decades are brilliant as far as looking for radio signals. It might not be that that's actually, we know what to look for in those signals, or we actually know yet, what the search volume is, or what other kinds of technology might be out there. So I think for me, the sort of first question we need to be asking is, what are we? And to that point, the great filter, I think there's another way that you could define the filter, which is that technology evolves on a planet. It's part of biological evolution. It moves into technological evolution. Whatever the physics is that describes us should describe all of that. And at a certain point, you have enough understanding about the universe to understand yourself. So there's a filter as far as your perception of the physical world and what you can actually detect out there, right? So gravitational waves, we didn't detect for 100 years after we understood what they were. When we understand what we are, we also have to develop the technology to do that. So there's a technological filter on our ability to actually detect ourselves. And so, or other examples of us out in the universe. So I think when we're thinking about sort of the technological phase transitions we're undergoing now, one of those key transitions is actually going to be artificial intelligence, because artificial intelligence is building systems that are like us, but not us. And they can help us understand ourselves in ways that we wouldn't be able to do without them. It's a little like, when you invent the microscope, you can see a whole world of microorganisms. So maybe you were looking for that fish in that volume of water in the ocean, but you didn't realize that there were tons of microbes in there until you had the technology actually to see the life in what you were looking at. I think artificial intelligence is going to be critically important for us understanding ourselves, so that we can actually see that sort of volume of space that actually is life out there. And just one final point I want to make on this note related to not understanding ourselves. There's sort of this implicit assumption that we make that life is common in the universe. And I think that's really premature, because we actually don't know what the phenomena is. I'm very optimistic it's common, and that we'll find it. And the kind of things that we're doing are going to be really helpful in the long term for discovering what we are and actually finding other examples. But right now, we simply don't know the probability for the origin of life, and therefore we can't say anything about the likelihood of life on other planets unless we detect it or solve the problem of how life arises in the first place.
I want to touch on a point you were making, Sofia, which is about whether certain stages of a civilization or some intelligent life's development are incidental, or whether they happen for all intelligent life. For instance, someone might think that all civilizations necessarily originate from a planet or a moon, but perhaps as you move further away from their origins, and this gets to what you were saying, Sara, although you were saying this about their very origins, into more complex features like organism anatomy and culture, the less likely you are to see that kind of convergence. And so I want to ask all three of you, especially as it concerns our topic today, whether you think that climate change or extreme biodiversity loss, or pick your favorite kind of extreme ecological crisis, are just inevitable steps on the civilizational ladder, something that just always happens when a tool-making species first industrializes? Or are we enabling ourselves by thinking so, by pretending that our specific choices, our preferred modes of relating to the Earth and its other inhabitants, are universals?
Well, let me just make a comment there. We used to be very fond of quoting Arthur Clarke's third law. Any sufficiently advanced technology will be indistinguishable from magic. But today's philosophers are actually posing that any sufficiently advanced technology will be indistinguishable from nature. And I'm quoting Carl Schroeder there. And I wonder if indeed those two examples don't indicate the arc of our cultural evolution, and that there may be a commonality in that, because it takes an aggressiveness and a curiosity to get us intelligent in the first place. But if we don't overcome that aggressiveness, we're not going to have a long future. And so if indeed you get the evolution of cultural evolution as well as biological evolution, and that cultural evolution allows you to act in a way that is not as aggressive to your fellow creatures, but allows a state to set rules and enforce punishments, then I just think that might be a common arc.
I guess I'll jump in next here. So it's hard to say, right, one way or the other, whether we are an example of a common civilizational arc of intelligent life, or whether we're an outlier. But I think it is interesting to see where the work has gone in the field. And so one kind of common framework that we use is the Kardashev scale, this idea that you can quantify the some sort of intelligent civilization by how much energy it consumes. And this is very useful. It's a useful framework for trying to figure out what kinds of intelligences our instruments are sensitive to when we're doing searches. But I think it also illustrates the way that we think about the evolution of other civilizations, which is that there's some sort of resource consumption, energy gathering, energy use that is expansionist, that is accelerational, and this very well maps onto what humans have done. And so there's been a lot of work in that area, thinking about what's the most efficient way to collect energy. Where would you want to be in the galaxy if you care about collecting energy? And there hasn't been kind of a commensurate amount of work thinking about what if that wasn't your goal as a civilization? What if your goal was to live sustainably with your planet and you didn't have ambitions to collect as much energy as possible or extract as many resources as possible? Now, there is an argument to be made that the most extractive civilizations might also be the easiest to detect, but I think there's a hole here where we need to think about what would a civilization's evolution look like in harmony with its biosphere if it wasn't being as extractive as possible. And that's important, not just for understanding what sorts of extraterrestrial intelligences we might detect or we might be missing, because we're missing the sustainable ones perhaps, but also important as a mirror to figure out what our civilizational track might look like and how we could use our imaginations of what other civilizations might do to improve our sustainability and relationship with our biosphere.
So I think maybe when we're thinking about these problems, it seems like there's two issues when we build narratives about ourselves or when we're building narratives about what other intelligence might be out there. And the issues are that we focus too much on the nature of the individual and we focus too much on the nature of our particular point in time. So individuals are special and our point in time is special. And if you remove those kind of assumptions from how you're trying to understand what's happening now on this planet and what the implications of it are, and you think over much longer timescales as we do as astrobiologists to think about the coevolution of life in this planet over many billions of years. And you also realize, as Jill pointed out, that there's cultural evolution and collective phenomena happening in human civilizations and with our technology right now. I think the narratives that we build from that understanding are quite different. And I think that there is some indication that long-term sustainability is possible, and the kind of hiccups we're having now are things that feel very existential to us because we're talking about them a lot. And usually I tend not to worry about the existential threats that we talk about a lot, because it means it's on our sort of collective consciousness that these are problems and they need to be addressed in the near term. And so I would think like the greatest existential threats to civilizations are the ones that we're not actually thinking about because we're not even aware they exist. And so I think long-term thinking is actually critically important for having a proper dialogue, which I think Sofia and Jill already alluded to, but I just wanted to stress that point.
Yeah, this question of long-term thinking, Sara, is so hard now when things are changing so rapidly. Now, 1,000 years ago, you're going to do what your parents did, right? Because things weren't changing culturally. But now it's very, very difficult to establish a mindset where you can think in terms of a long future.
Yeah, but I think part of the thing is like that information is getting integrated at a scale individual humans aren't aware of anymore. So because our technology and we as people are so integrated, some of that processing is actually happening at a societal scale and not an individual scale. So I think there's always sort of a level that's actually keeping in pace with the sort of longevity of that system. It just might not be us anymore. And culturally, we have a lot more idea what's going on than we do as individuals. So I agree. I think for us as individuals, it feels very fast, but I don't think for sort of technological evolution, what's happening right now is fast at that scale.
Let's return to the Fermi Paradox for just a second. The Fermi Paradox that we've all resoundingly rejected. Suppose that we wanted to use today's technology, I'm going to ask you about some speculative astronomy a bit later, but just stick with today's technology to have a better sense of Fermi's paradox, whether it is actually in fact paradoxical or just provisional. And imagine you could commandeer the budgets of NASA, the NSF, the ESA, Roscosmos, whatever, and whatever other bucket of money, various billionaires there is out there to search for intelligent life. What would you want to do?
That one is something that we talked about at the turn of the century when we published SETI 2020. What would we like to do? And the thing that we realized is that over all these decades, we've had essentially zero sensitivity to transient phenomena. So our answer to that is you want to look at all the sky, all the time, and across the entire spectrum. And we're beginning to make it, finally, decades later, make it a start on that with some optical SETI searches that will look at 10,000 square degrees of the sky at the time, or in fact, all the sky all the time with laser SETI. And in the microwave with the Malura wide field array, it's a start, but that is what you'd want to do. If you had infinite budget, you would really want to be looking at all the sky all the time, at all frequencies, and you'd want to be developing as unbiased machine learning algorithms as we can build to take in this fire hose of data. So the other thing we've been doing since the beginning is asking machines, does this pattern exist in the data? But we really want to be asking, are these data information rich, or are they just noise, and not be prescriptive about what we're looking for?
So I have quite a different example, which is just coming from the other end of the spectrum. So I think Jill's suggesting we look for technology and look for these kind of unseen signatures of it. I think we need to build better origin of life experiments. And what I mean by this is we need to do it at scale, where we have international collaboration, multi-billion dollars to actually explore chemical space using digital robotics and sort of the robotic, like there's a lot of digitization of chemistry and chemical experiments at scale. And part of the reason for that is if you build a planet simulator on Earth, that is a geochemical engine that is evolving chemistries out of it. And then you actually are exploring those for the emergence of lifelike or intelligent chemical systems. You are actually building a platform for constraining the value of the P-life term in the Drake equation, right? We don't know the original life term. We don't have any constraints on it, but we can actually start to bound that probability by doing that. And we can do that here on Earth. And we have a lot of the technology already to do it. And we have a lot of the theory to guide that kind of experiment. And I think if we do that, it's a really different way of talking about the search for intelligent life, because we're basically trying to grow it in the lab from scratch. But those life forms, if we do the experiments right, would be as alien to us as anything that we might find off Earth. And it would be under a set of conditions where we really could start to understand the process. So for me, that's the number one, because it would solve the origins of life and allow us to have some constraints on what we're looking for elsewhere.
So Sara, do these models have feedback in them?
So a lot of the ways that we talk about doing these things is actually like a recursive exploration. So if you imagine that you had an AI that was like actually partially physically embodied in a chemical system and sort of abstractly embodied in AI, and it was doing a recursive search of chemical space, you would actually be able to kind of curtail the combinatorial explosion and actually search along directed pathways. So there's some way of building intelligence into the exploration to look for other intelligence, but I think it's within the realm of possibility. There's a lot of people interested in this. I don't think that, like we think software is intelligent, but software is not embodied intelligence. It's not the same as us. It's something we invented and it's very abstract, and it doesn't have quite the same properties as chemical intelligence does.
So I wanted to take a totally different tack with this one. And this is partially inspired by the Astronomy and Astrophysics Decadal Survey that came out kind of within the last week or so. And something that's really interesting is for these big like surveys, state of the field, like all of the money of like the giant federal funders looking for the next 10 years, there's a lot of focus on missions. Like what kinds of instruments can we build? What kind of surveys can we design to get as much data as possible to learn more and more about our universe? Don't get me wrong, that's fantastic. But at least for searching for intelligent life in the universe, there are many existing data sets that are kind of untapped, and many ideas that people come up with and say, hey, technology might do this. And if it does that, it should be detectable like this. And then no one ever searched for it. Papers that came out decades ago. And it's there are many reasons for that, but partially it's been just a lack of funding and a lack of a community to follow up these ideas and to discuss these ideas. And I mostly work in radio wavelengths, but the more time I spend in the field, the more I realize that we really need a very diverse, both in the participants and the science that's being done, portfolio of extraterrestrial investigations. So that's things like, we should look for Dyson spheres, but what if extraterrestrial intelligences don't make Dyson spheres for some reason or another? Then we should be looking for radio signals. We should be looking for intelligent species that pollute their atmospheres the way that we've done to ours, but we shouldn't be maybe putting all our eggs in one basket. And so I think what I would love to see is just more support for kind of furthering all of the different avenues of searching for intelligent life, because right now we don't know which one is going to succeed. So we want to make sure that we're following up all of the possibilities, and also just support for kind of new blue sky ideas on what intelligent life might be like, what technology might be like, inspired by things like artificial intelligence and synthetic biology, where we can go down these kind of rabbit holes of, okay, what if we're the weird ones? And most life is like this other thing we haven't even conceptualized yet. What signatures would that leave? And so I think that's something that kind of, with infinite resources, I'd love to see so many more minds getting involved in this project, so many people collaborating on very different ideas, both ones that have already been theorized and ones that we've yet to come up with.
Let's, those were outstanding answers. Let's indulge in a little speculative astronomy. Imagine astronomy as it's practiced, say, in the year 3000. Do you think by then, or at some future date, with a massive telescope or several, leveraging some local lensing effect, it might be possible to watch a bunch of civilizations, assuming that a bunch of civilizations exist across the galaxy in sufficient detail to see how they evolve over time. You know, there's already theoretical work on how we might be able to zoom in on exoplanet atmospheres, of course, and spot everything from pre-agrarian civilizations to planets that are covered in cities, to those engaged in nuclear war. And I'm wondering if we might be able to use techniques like that to develop a kind of grand census of civilizational outcomes, or would that kind of knowledge only be possible with contact and cultural exchange?
Ross, I think you could do it in a statistical sense. I don't think you'll ever do it by finding a single example and waiting around and continuing to observe it to see how it changes. Because, you know, we have a finite lifetime and we're pretty damn not very patient. So I think that you could probably do it the way we have done, constructed the story of how stars and planets form by looking and finding lots of examples at different phases. Now, we have with the planet and star formation, we have confidence that the physics is going to work the same everywhere. So we can put apples and oranges together in a time sequence and infer evolution. I don't think we have that kind of confidence necessarily in technological evolution or the evolution of cultures and species, but we could try. I don't think you'll ever get there by studying just one, but statistically with lots of examples, we might be able to try and answer your question.
Yeah, now I'm thinking about like trying to infer general theories of economics from observing exoplanets. But I think that's the right way of thinking about the problem, though. If you have enough data points, you should be able to reconstruct the general principles. Yeah, I agree with that.
I definitely find myself somewhat skeptical that we could get the sort of data we would need to really understand what was going on with another technological civilization on a planet. So I think maybe, you know, given this kind of example where we can observe a lot of different civilizations throughout the galaxy, we could get some senses as to what might happen, potential just outcomes or almost states, potential states of planets. But I think without some sort of contact or exchange, which of course, given the distances between things is very difficult, it would be hard to understand the why and the how. I think a statistical census would be the only way to go about it. So totally agree with both Jill and Sara on that. But even then, I think it's so easy when we, as humans, to project our kind of biases onto whatever we're trying to observe. And so sometimes that's, you know, observing animal behavior and attributing kind of anthropomorphic ideas onto that behavior. And I think you would see a very similar thing where we see like, oh, there's a civilization on this planet and we can measure the temperature going up and up. And we can say, oh, well, that's an example of global warming, and global warming happens because of these reasons. But I think that would be going a step too far. We don't know that that's why a planet might be warming. And so I think even with really good observational information, it's hard to understand something as complex as an intelligent species interacting with its planet, interacting with its technology, from just passive observation and data points. But maybe I'm wrong about that.
Sofia, you know my favorite example of this, I think, which is given the budget that you say, and these fantastic telescopes will build something that can actually image those 7 Earth-sized planets in the TRAPPIST-1 system. And they're at different distances from their host star. So physics tells us they should be at different equilibrium temperatures. But suppose we can image them and we see that they all look the same, right? They're all at the same temperature. They all have the same albedo. They all look identical in our fantastic telescope of the future. What does that tell us? Is that a way of deciding that you've got a technological civilization there that wanted some more real estate. So it went to the next planet over and made it home.
So there's one more thing here that I think that we need to take into consideration, which is how convergent is technology across different examples of life, which I think Sofia might have touched on a little bit. But, you know, there's a lot of assumption that, you know, if we're looking for alien life form, even at the chemical level, it'll use the same molecules that we use on Earth, right? So we use amino acids to, you know, look for life in the solar system, or we look for oxygen as a biosignature on other planets, right? So, but if you think about the size of chemical space, like the number and diversity of molecules possible, it's exponentially huge, even for small molecule chemistry. So, so it's realistic to say, if like you think of life as a general process and not a chemistry of life on Earth specific process, or a technology of life on Earth specific process. If you think of it as a general process, if you have geochemistry on a planet and you're exploring this huge combinatorially diverse space, already at the level of chemistry, you should see some divergence between what chemistry you see as being biological on one planet and what you see on another. And that will form some kind of statistical scaffold that then you would expect the evolutionary trajectories to be completely different on those planets. And if you think about the space of all possible technologies, it's even exponentially larger than the space of all possible chemistries. So to think realistically that there's going to be some convergence in technology is, I think, really premature. So I made the joke about economics, but you know, money is obviously like something that was invented on Earth. It's not a physical thing. It's an abstraction that our civilization invented, which happens to work very well. It might be that, you know, the only planet that has economics is our planet, because it's just so unique to our particular space and our particular trajectory of evolution through the space of what's possible. So I think we have to take those things into consideration when we're thinking about, you know, what are we going to see out there and how can we build general models, which goes to the points that were already raised.
Yeah, Sarah, we've just seen a recent example of getting into trouble that way with the phosphine announcement.
Yes.
On the Venus, where the original authors actually went so far as to say that they had explored all chemical space, and there was no way to make that phosphine without some biological component, and that's just such a difficult thing to.
I think that way of pursuing the life detection problem is an impossible uphill battle, because I don't think you can rule out every other explanation besides life. I think you have to have an explanation that it is life, and then you have a real hypothesis that you're testing, and you know, it's sort of so yeah, I think but part of the reason I would make that argument is because of the combinatorial space that life exists in. Life is chemical for a reason. It exists in this high dimensional space that's very hard to navigate through, which is why life requires information to do it. And that information is specific to the molecular architecture it has. It's a good example.
I want to, since we are thinking far out in the cosmos, but trying to make our speculations, our cosmic speculations, bear on life on Earth here, I'm going to ask the three of you to suppose that we do make contact and we do have some cultural exchange with another civilization, and it is semantically legible by some miracle. And that this civilization is likely an older civilization. I know that there's been some deserved criticism of the notion that these cosmic others would be like gods dispensing wisdom to humankind, but suspending that criticism for just a moment, what question would you ask them if you only had one and you were hoping that their answer could improve our prospects here on Earth?
Well, you need to watch the movie, right? Because that question is in there. It's how did you survive your technological adolescence? How did you make it through?
It feels like a big question to just come up with an answer on the spot, but
we only got one question, so I'll make it a big one.
My kind of off the cuff answer would just be, how common is life and how common is technological life? Okay, maybe a two-part question. But I think that from that, you can infer a lot about the difficulty of evolving and surviving as a technological civilization.
I would ask, how does it feel to be you?
Alien qualia. Love it. Before we get to some audience questions, suppose we never find intelligent life, or we have good reasons to know that there is no one else, or that simply that civilizations are just too widely spaced in the cosmos. They're like one every 100 galaxies, and we have no hope of ever kind of coming into causal contact with them. Given y'all's choice of profession, I'm sure that would come as a disappointment. It would come as a disappointment to me, I'll say. But how would it make you think differently, if at all, about our human existence?
I keep going first. It would make me really, really take seriously how important we are and how we shouldn't mess this up, right? If we're a rare example of an intelligent species, then we owe it to the cosmos to stick around and not do ourselves in.
So I finally gave myself a more optimistic technical argument that's kind of in the vein of what Jill is saying, actually, which is, cosmologists like to count the number of degrees of freedom in the universe, right? And so we know the universe started in a low entropy state. And then if you actually could count like how much was happening on this planet as a very unique planet, I think it would probably outweigh everything else we can observe in the rest of the cosmos, just because of the chemical diversity, biological diversity, technological diversity on this planet, right? So in some sense, more is happening on this planet than what we know of is happening in the rest of the universe combined combinatorially. And so if you buy these arguments about sort of life being this creative process that is actually generating complexity in the universe or generating more novelty, then then that process is really happening here. And it indicates that there's sort of a long technological future for our planet, because it's an explosive amount of creativity and things happening in our long-term future. So I guess it kind of at least gives me hope that the technological future on Earth is long and bright. If we're the only one. And so I guess that's kind of a little maybe too cosmological for most people's taste, but I think it's actually really important to think about our place on that scale. And I think, my other sort of opinion, which is probably more controversial, is I think most of our cosmological models are failing because they don't account for the physics of technology. And so the long-term future is maybe quite different if you take that into account. Mm-hmm.
Yeah, I think the optimistic take on this is exactly what Sara said, that if life is really that rare, then we're in the most interesting place in the universe, or in every 100 galaxies. And we're here, we can take advantage of that. We can understand these really rare states of biology and chemistry, physics you couldn't observe anywhere else in our galaxy. And that's kind of cool. And I think from another standpoint, and maybe this is my physics brain, but I would be so curious if we were able to make that determination, like what's going on in the rest of the galaxy then? If it's not life, what is it? And does it just mean that the solar system is really just this perfect special place to be? What makes it so special? I think it would really change our astronomical understanding as well of like the context of planet formation, of star formation, of galactic evolution in really interesting ways. And so I don't know if that's quite as interesting as the implications for kind of the future of humanity, but I think it's kind of fun to think about.
So Sara, I'd like to pick your brains on synthetic biology for a second. I used to say that we'll never be able to understand what is necessary versus what is just contingent in terms of biology, the biology of life as we know it, until we find a second genesis, another biology. But then people have been arguing with me that say, no, we're getting somewhere with synthetic biology, and we may actually be able to answer that question, necessary versus contingent. And are there other ways to make life?
So I think it depends on what you qualify as synthetic biology. So I think sort of current synthetic biology, where we're trying to build cells from known parts, is actually just an extension of life. So that goes into the contingency issue. And so is technology. So this is actually a big problem in the origin of life field. It's really hard for us to remove our agency and our timeline from the experiments we design. And so in my mind, anything we build is actually an example of life. That's part of the same example of life we are. Because of that, you know, we had to evolve and form on this planet before we actually designed experiments that we're now trying to test principles of life. And so those experiments we're doing are actually examples of life too. But I do think it's possible to reduce the amount of information that you put into an experiment and basically control for how much information you put in, and then try to evolve synthetic life from scratch, which would have controlled sets of contingencies that you put in the initial part of the experiment. And then you can actually see how much physics generates for free without you actually designing it yourself. Because we are physical systems and we are designing physical experiments. So we're putting the design in. We need to actually remove as much of our agency and our information as possible and then watch that process happen. So I do think it's possible to happen on Earth to remove the contingency of our evolution, but we have to be very careful about how we talk about it and how we design the experiments.
Okay. Okay, I think Jonathan is going to join us with some questions from the audience.
Yes, thank you, Ross, and thank you to the panelists. We have a few questions, and we still are inviting more if anyone would like to add them to the Q&A panel. But we're going to start with Mike Antares, who has asked a rather broad question, which I think could lead to some good conversation. What are some of your favorite thought experiments or questions when it comes to potential contact with life beyond Earth?
Okay, let me jump in again. I've been struggling with some talks that we've been having at the SETI Institute. We used to say that mathematics would be the means by which we could communicate with another intelligent technology. But that's not so clear to me now, because at least the way we express mathematics apparently is determined by the structure of our brain. And that it's possible that indeed another technological or intelligent civilization might have mathematics, and they might be expressing the same kinds of things that we're talking about, but we wouldn't recognize it as such because their mathematics would be so different from ours because their brains are differently structured.
Anyone else have any thought experiments?
Well, So I might not answer the question directly, but Jill brought up my favorite example of thinking about physics of life, because I actually have a very similar view that mathematics is not universal because it's an invention of human minds. And part of the reason we think it's so powerful at describing the physical world is because we can communicate it so effectively. And also we can communicate it between us and our technology. So it's like this particular kind of information that's easy to propagate in our biosphere and easy to retain its properties and its meaning. And so I think actually when you invert these sort of canonical biosignatures, like we always thought math was gonna, it would be the same math we have, or it would be the same molecules we have. And then you ask questions about what does that look like from the outside? And how should I think about those things if they were being generated by a general physical process? I think we start to get some real insight. So my set of thought experiments I do on mathematics is to do what I call a physics of theoretical physicists, which is like if you're asking questions about what does theoretical physics look like generally, I think you start to get new ideas about how to think about that problem. And what it might look like on other planets, even if it doesn't look like what we look like at all, which is again going back to this idea that we need to be able to recognize the unknown physics of us. But I don't know in full detail what all those signatures look like. we have one sort of candidate from some work that we're doing on physics of life, which we call assembly theory, which is trying to get at the idea of detecting complexity, particularly in molecules, as a biosignature. And the idea there is like, if you take a molecule and you break it in half again and break it in half again and break it in half again, you basically build this giant tree-like structures of all the ways of assembling the molecule. And if the shortest path in that space is sufficiently long, it suggests you need an information processing system to build it, because random exploration of that combinatorial space would never get you to this one specific complex molecule in high abundance that you would actually ever observe it. And we think the same thing for technology. So there's some people don't think about molecules as technosignatures, but there's some molecules like Taxol that are so complex that you would never expect anything but an intelligent civilization to be able to produce them. So I think if you just think in chemical space, like there's these boundaries that only living physics can cross. And then when it achieves what we call sufficient intelligence for technology, there's certain molecules that can only be produced that, then you start to kind of see, what the physics of life constructing this possibility space and actually making these things that you would never expect to see otherwise looks like.
Sofia, do you have a thought experiment for us as well? I mean, it seems like we started with a thought experiment that in a sense, that's what the Fermi Paradox is. It's one way of looking at it. What would you pose as a thought experiment?
Sure. So I don't know if this is quite a thought experiment, but something I've been thinking a lot about lately is I recently published a paper about the signal that was investigated by the Breakthrough Listen group that we were calling BLC1. And it was something that looked a lot like what we would expect a radio signal from space, from an extraterrestrial intelligence to look like. And it took a lot of work, almost a year of my professional life, to track down what was causing it. And in the end, we can attribute it to human technology. So not an alien signal after all. But that process was long and it was slow and it was complicated and it required us to develop new methods. And I think the case study of phosphine on Venus, that purported detection, is also a great example of maybe what might be sort of a spicy take, which is that first contact will probably be boring in that for us to find and verify extraterrestrial life, be it kind of microbial or intelligent, is going to take years and years and years and dedicated instruments and time and back and forth in the literature and extremely detailed statistical analyses and things that just aren't particularly interesting to the average person. And it'll take us a long time to come to a consensus if we ever do. And that the information that we get from that process will take a long time to parse in a way that is not quite like the UFOs landing on the White House lawn sort of view of first contact. And so, especially with this kind of latest investigation that I did, it's a reminder that science is long and complicated and easy answers aren't always going to be there. And so what will our reaction to that sort of first contact scenario that is complicated and ambiguous and boring look like might be an interesting thought experiment on its own.
Ross, you're writing a book about the Fermi Paradox from what I understand, and wondering, well, first of all, is that true? And if it is, maybe you would like to announce it to all who are listening. I'm sure will be avid readers, but also in light of that, what would you see as a thought experiment that might be of interest given this context?
Yes, thank you for giving me a sort of free moment here to plug my book, which is not about the Fermi Paradox, and in which I hope to actually go the length of its 300 pages or whatever without actually mentioning the Fermi Paradox. It is tentatively titled The Long Search, and that's based on the idea that it's about the search for extraterrestrial intelligence. And it's, my sense, which I suspect is shared by many here today, is that that search is going to be with us for a very long time. Not because it won't be successful, but because it's going to be an area of interest for humanity as long as humanity is around, and that we sort of live right at the dawn of it, and that this is kind of as such, a moment worth recording in some kind of literary and philosophical detail. And so in terms of a thought experiment, one thing that, if you'll allow me to sort of steal the microphone, the question asking microphone back, and put a question to our panelists. Given that we all arrived here promising to discuss the Great Filter, but skipped right over it because we don't buy the underlying Fermi Paradox, I wonder if I might ask our panelists to assume the Fermi Paradox is interesting and valid for a moment, and that the Great Filter is a compelling way of thinking about it, of some of the explanations for it. And famously, people who have kicked around the Great Filter have said that, the filter could be in our past, which is to say it could be the origin of life, or sexual reproduction, or the Cambrian explosion, or it could be in our future, which is to say that we are kind of bumbling towards some existential risk that is in our blind spot. And I wondered if our panelists, if they would indulge me by entertaining the Fermi Paradox, if only briefly, could tell us whether they think a filter would be in the past or the future, and which one would strike them as most likely.
I always think it's probably at the origin of life itself, because I think once life gets going, there's some explanation for why it's done the things it has. But I tend to think about that transition as sort of, like NP hard in a computational sense. It's actually really hard to calculate what the probability of transitioning from non-living to living matter is, because it's actually transition in the physics. It's a little bit like the quantum to classical transition, and identifying that sort of exact boundary is quite hard. So I think that event is actually the hardest one to constrain, because the rest of it, at least from my perspective, and obviously I have kind of a very biased perspective being a theoretical physicist and looking for universal principles, I think the rest of life is kind of explained by the same principles. What you want to know is, why does that physics take over in the first place? And I think that transition is quite hard.
Are you, in holding that position, are you troubled at all by the fact that life appears to have gotten jump-started relatively quickly on this planet?
No, it doesn't bother me at all, because that's an artifact of post-selection. So, I mean, people that do proper probabilistic assessments of the origin of life probability based on the fact that we would have to be here, like we are contingent on that event, right? So if you post-select on the fact that we wouldn't be here without an origin of life event, you actually can make arguments it's very probable or very rare based on the fact it's super quick. So you can get very super quick transitions if you post-select on them very easily, which means you already have the end state. If you have the end state, it's easy to say something happened fast.
And Sara, isn't it correct that if it takes a long time to go from microbial to mathematicians, then we couldn't be here unless life had started very quickly?
Right. But yes, that's exactly right. But if you think of it as an entire distribution of possible values for the origin of life event, right? Like, and how quick it is, and you make your argument, you're already selecting on some tail of the distribution, right? That is the one that happened fast. And if we only have one example, we don't know if it's closely distributed there, or that is some very rare tail of the distribution. There'd be no way of assessing. And so that's sort of how that's built into these probabilistic arguments.
Well, we are at the end of the hour here, and a fascinating panel, which actually has teed up in some very interesting ways where we're going next. But I'm going to turn this back over to Bill for a moment, since he is bridging us from one section to the next.
Great. Well, thank you, Jonathan. And I mean, what a inspiring discussion. Fantastic. Sara and Jill and Sofia and Ross, that was wonderful.